Hi guys, today we're going to continue with our third program, our third tape on standard electrode potentials. Now, I've gone through two types of standard potentials. One is standard electrode or redox. Here I say redox, okay, because it concerns oxidation reduction. Redox potential and standard cell potential. So for standard electrode potential, just let me go again, is the EMF of the half cell or the test electrode compared to must be a standard hydrogen electrode. Okay, so that is called standard electrode potential. So we develop the whole thing there, all the table of values, all this part here. If you want to look at it again, all right, like here, this whole series. Oops. It's here. Okay, this whole series here. Oh, sorry, I didn't prepare for this. Okay, and this whole series here. All right, all this whole series is developed with this part being the test electrode to you, right? All these things here. Right, and all these things are written in, they are positive, which means they are all positive whether they occur or not, because they're written in the reduction potential. So it's called the reduction potential. Okay, so all these are the signs are written in reference, and the magnitude is reference with hydrogen. Okay, so now I'm going to talk about the three uses. Here they actually sort of tell you, but I want to put it in correct perspective. Okay, I just want to put down the time. So I don't have to shoot time. Okay, so the first use, you can see here, if you go accordingly, right, the use of this thing here, the E naught. We call it E naught or E standard, okay, is to find, here is to calculate, here, first one, is to calculate the standard cell potential of combining two standard electrode potential, means anything. So find the Emf of a cell, that's all. Okay, of course, the famous one, of course, is the Daniel cell. I think 2L, right, when you have the copper and your zinc both in the solutions. Okay, go through first. The second, of course, is to predict the reaction. Where's it? Yeah, number two. Predict the feasibility of a reaction. Now, this reaction is not any reaction, right? It's a redox reaction. Okay, because there must be electron transfer. So to predict a redox reaction, will it occur or not? Okay, so we'll look at that. And thirdly, of course, the third one is here, to deduce from the E naught values the relative reactivity of the elements of group 17 or whatever as oxidizing agents. Sometimes they might ask you to turn around as reducing agents. Okay, so there are three things we are going to consider today. So hopefully in 1 hour's time, we can actually fulfill all this, okay? I've done, all the answers, so I just go through them. So for you, you have to go again with the video if you need to clarify some things. Okay, now the first one, of course, is here, is to deduce or calculate or find the EMF of a cell, right? Now I've put down here, sorry, I won't go to this, I'll go to the one where I left out last week. Okay, now here we got, first of course, is to define standard cell potential. Remember, it's the EMF of any two half cells, right? Any two half cells, right? Connect together to form, under standard conditions, okay? The cell means any two, right? Any two. I'm going to put this thing first. Okay, as you can see here, is it here? Is it here? Is it here? Is it here? Okay, right. So, okay, standard cell potential. Right, put the ink first. Okay, standard cell potential. EMF of a cell composed of 2 electrodes or 2 half cells under standard conditions. Okay, so don't have to be halogen electrode. So let's go to here. All right, now I left off this one here. The following incomplete diagram shows that apparatus can be used to measure the EMF or the E cell. Okay, standard cell potential of a cell composed of iron 2, 3 plus and 2 plus, Ag plus and Ag half cells. Now they put like this. So complete it. Well, of course, here you need to put what? The voltmeter. Okay, so and then the salt bridge. So what must be labeled? Okay, voltmeter, and this is the label here, salt bridge. Salt bridge actually is any solutions that contain soluble salts, which do not react with the solutions. So normally potassium nitrate, right? Because why? All nitrates are soluble, so they will not cause a PPT. Potassium salts are soluble, so okay, or sodium nitrate for that matter. Chloride a bit tricky because some chlorides are insoluble. Okay. Okay, so sulfate, so some sulfates are insoluble. All nitrates are soluble, so this is used as a salt bridge. Okay. Now it depends on what you want. Okay. Now I'm going to look at the marking scheme here. Complete diagram as to label components, blah blah. Identify A to D. Right. Okay. Now here they say, all right, voltmeter and salt bridge 1 mark. Okay. Now A, let's say is silver here. Okay. So let's say if A is silver. So here would be, of course, silver nitrate, or just put silver ions. 1.00 mole per dm cube. That's the best. Okay. So if A is this part here, the silver ions, here will because it's F+. Now. So here, remember there is no metal, so C must be platinum. And D must be a solution of the 2 salts. So the best, of course, put Fe2 plus concentration. This represents concentration, okay? Concentration moles per dm cube. But you must still put it 1.00 mole per dm cube, okay? This Fe3 plus, 2 of them must be present. 1.00 mole per dm cube, okay? You need to write this surface down here, okay? So all is written down here, right? So keep the marking scheme, right? Voltmeter and bridge 1 mark, silver 1 mark, okay, this 1 mark, platinum 1 mark, okay? Well, it's 4 maybe 1 mark, okay? This one, this and this 1 mark. So they didn't put the 1.00, but you put anyway, all right? Okay, you can reverse the thing here. So now here, use the E naught values. E naught values means, of course, the SEP. Okay, the table M, to write the equation of the cell reaction are equal, means the overall equation. Overall equation for the cell reaction, which takes place when the 2 electrodes are connected by wire. Right, obviously now here I told you already, to write the equation here, you need to first determine what, or to deduce, or to find what? Poles. Poles is the key thing, the poles. Which is positive, which is negative. Of course, to find which is the poles, obviously you need to look at the here, silver, all right, which is positive, which is negative. If 2 are positive, it means which is more positive, it's positive. If 2 are negative, which is more negative, is negative. Okay, it's because it's relative. So silver is on the raw. This is called raw readings. Okay, raw, that means original readings. Okay, so iron is how much? F plus and 3 plus. Okay, iron is plus 0.77, plus 0.77 and plus 0.8. So of course 0.8 is more positive. So silver is more positive. So silver is positive. Okay, while iron, which is 0.77, is 0.8, just more by 0.03. So it's negative. So in that case here, after that, to decide where the direction of electrons. Direction of electrons. So obviously from negative is a source of electrons moving here. Okay. So obviously what is happening here would be your oxidation. Okay. All right. So is oxidation, what is the reaction? Of course, that means Fe2 plus must be going to Fe3 plus electron. Now, I said there are 2 ways to find the E cell. All right, in this case here, if you go reverse way, right, is positive 0.77, as you can see here, right? Fe2 plus, Fe3 plus, Fe2 plus, okay? Here, positive 0. So you go the other way. That means you got to change your sign. All right, so it will be minus 0.77. Okay, then of course, this case, silver here, it accepts electrons. Okay, that means it's undergoing reduction. So silver positive plus electron. You don't have to put the states, I mean, it doesn't really matter in this case. Okay, silver. So in this case, originally is positive 0.80. So you can get two things from this kind of working out. You can get the overall equation, which is silver positive plus Fe 2 plus positive to give you silver. Write the same things first, silver plus Fe 3 plus, okay, because you cancel out the electrons here. So you just add here, we do E cell equals to minus here is 3 plus, it should be positive. Positive means that can happen. Okay, so you can see that this is the direction here. Okay, right? So 1 mark here. Okay, silver is deposited. Okay, then, so this is any cell. So this is a cell. Cell, any kind of cell will do. Okay, now the other one, of course, this is between a metal and ions or metal, and then two elements with different oxygen states, right? And here, of course, is another one here. Okay, here, right? Another partial questions. Chlorine gas and iron, two ions can react together to in equation. Now this one is called redox reaction because here I got only chlorine, right? It means that I got a solution here, okay? I bubble into here, chlorine gas, Cl2 gas, and this is a solution here. And this solution contains Fe2 plus. Remember, there are no Fe3 plus here. No Fe3 plus, and there's no Cl minus here. Don't have. So only these two fellows here. That's what I mean by a redox reaction. In the cell, there will be everything. There'll be this one here and that one here together under one half electrode. This and this present together. So in this case, it's called a redox reaction. I've got only these two to start with. These are my reactants. Okay, later look at it, okay? So here the main diagram, the front diagram shows the apparatus needed to find the E cell, the EMF of the cell, okay, of the birth reaction. So in this case, I have the cell. So if the cell is like this here, of course, the arrow here misses must be gas, that means must be chlorine, okay? Otherwise it cannot be iron, otherwise not gas one. So it's Cl2 gas here. Of course, in this case here, I must also present Cl minus concentration equals to 1.00 mole per dm cube, okay? It can be sodium chloride, up to you, anything that is soluble, okay? 1.00 mole per dm cube, or potassium chloride for the matter, right? So in this case here, I have my iron 2 iron 3, so this is, since there's no metal for a solid transfer electrons, I must put platinum here. And of course, this E will make out of what? Two things here, Fe2 plus, okay, and also Fe3 plus because it's a cell, mole per dm cube, okay, and Fe3 plus here, 1.00 mole per dm cube. Okay, now that's how you determine it, all right? So use the data booklet to calculate the E cell. Okay, see now? So this is the use of your standard electrode potential. Okay, so to use the data booklet, use what the E naught to find the E cell, and hence deduce which direction. See, right? The comes of flow, very simple. Okay, as the switch is on. So basically, as I said, the first thing you need to find is the poles. Again, poles. See, poles are very important. Get into your brain. Poles. After poles, can find the direction of electrons for you, right? Okay, poles. Silver, chlorine, and Fe2 plus, 3 plus. Okay, very simple. Chlorine. Chlorine, you take the original raw things here. Okay, the system is here. So original one is plus, very big plus, 1.36. And of course, as I said, the other one is Fe2 plus, Fe3 plus, check again so I don't get caught. Where is the flag? Wrong one here. Okay, run up 2 plus 3 plus. So here is a big one, right? Put down here plus 1.36 because I can't see when I scroll it up. Okay, Fe2 plus Fe3 plus again is plus 0.77. So which is more positive? Chlorine more positive. So chlorine and chloride will be positive, all right? And Fe2 plus Fe3 plus will be negative. So this is positive, this is negative. So once that's decided, oh, negative means what? Electron, source of electron flow from here. Okay, so electron move from here. So it's a put the arrow here, electron flow. Okay, this will give you the mark. Okay, so in this case here, once you get that, of course, you can find the E naught and the equation. Okay, they say blah blah blah. Decide which direction the flow. This one, this one. Okay, of course, you can do the whole thing. Right. So very simply, negative is negative sign here first. Negative, of course, negative is what? Negative is so electrons. It means Fe2 plus, right? Must be undergoing oxidation. It goes to Fe3 plus electron. Of course, it's go this way is minus 0.77 volts, right? Because the other way, you can see again, I'm just trying to tell you, okay? The other way is positive. The reduction way, this way is positive. So this way, which is oxidation way, is negative. So here the negative, right? Now, of course, the positive sign would be, of course, chlorine, Cl2 plus 2 electrons give you 2 Cl minus, which is a very large positive, 1.36. I think so. Let's look at it again, 0.36 chlorine. All right, which is here, 1.36. See, Cl2 going to that. This is reduction here. So, all right, good for you. So, of course, you square them up. Remember, when you design the 2, it must times 2, but you don't times the raw E naught values, okay? We use blue color, so make it easier for us. So times 2, here times 2. Don't times 2 here. So you cancel off this one here. So the equation will be, I can put Fe2 plus or Cl, doesn't matter. 2 plus here, 3, sorry, plus Cl2 gives you 2 Fe3 plus 2 Cl minus, and of course the E cell. See, now this is the use of your standard electrode potential. You minus 1 here, carry 1 here is 9, the other one is 2.5. Okay, 0.0 positive. Positive means that feasible, that means it's going to flow. Okay, so here E cell is this one here. I think got the answer here. Okay, right. Now this fellow here, I start to say, is bad news, okay? But they don't care here, okay? See, it should not be negative because I don't know why I'm going to explain people's answer because he's after all CIE. But I show you where later it doesn't tally. Now let's say, okay, I want to do by another way, right? This is which is correct. We got it correct. Anyway, it's positive here. Okay, direction flow from where? Direction flow from E to B, isn't it? E to B. Okay, so E to B. Okay, as long as you label that correctly, right? You put the other, okay, E to B, right? Now, I told you the other way of finding this E cell is very simple. So use the equation. E cell is equal. Now, remember, this is the correct way, because you right and left, then you get mixed it. You don't know which is right, which is left. So always put reduction minus E oxidation. And this one here, you must make sure they use the raw values, okay? Don't change it. Here can change the sign on top here. Here can change the sign, okay? But here cannot, all right? The rule is, so E reduction, what is undergoing reduction? Of course, chlorine is, okay? Reduction. So what's the value? Bracket plus, okay, 1.36. Just have thermochemistry, the sign is very important. Minus, okay. What is this one here? Remember, originally is a plus 0.77, okay? So of course you get positive 0.59, okay? This is the correct answer, see? But the marking scheme tells you that is here minus now. So I wouldn't say I disagree, I really don't care. But, right, say ignore sign, but you should have a positive, show that it's feasible. I'll tell you why. See, later there will come another question like that. Okay, later. Okay, when we talk about redox reaction. Okay, now I got here interesting. I just cooked it up. Okay, now here I cut and paste so that it's not very nice diagram, but enough. I got two half cells here with the two famous oxidizing agent, KMnO4. This is your KMnO4. And this is your dichromate, potassium dichromate. Okay, two of them, of course, acidified. Okay, with sulfuric acid. Okay, so both of them are powerful oxidizing agent. Of course, this is more powerful. Okay, right? KMnO4 is more powerful, as you know later or after. Doesn't matter in organic chemistry, you will know. So you put them together, who is more powerful? That means who can actually, remember, oxidizing agent is one that will take electrons now, okay? Instead of being reduced. So who is more powerful? Of course, you can know. Later we see, you can know from the values here, of course. So I can see here. See, there are two MnO4 minus. You always use the one with 8. That means it's excess acid. You get 2 plus, here get 4 plus, here plus 4. Okay, so we want this one. Okay, plus very big, no. Plus means whoa, very feasible, very powerful. Okay, plus 0.5 and can take 5 electrons. Don't worry about the comparison, don't care. Okay, don't come to that first. Okay, and for your chrome and your dichromate, sorry, is plus 1, 2, 3. That means it's less positive. So if I've got this two here, compare, okay, I hook it up. Will they give me a value in my voltmeter? Yes, they will. They will form a normal cell. Somebody must be the power one to take the electrons. Somebody must be there to give electrons. There must be, because both can be same power. You can see called concentration cells, but don't worry about it. Like your father in your house, he's your father. But when he goes with your grandfather, he becomes a son, see. So, no, you even though this is a powerful oxidizing agent, right, it's on here, right, it's on here, it will be a reducing agent when you compare this one here. Now, what happens is this. As I said, both of them put here, so first of all, you determine what the poles. So who is more positive? Of course, dichromate. Why? Because you can see here, it is more positive, MnO4. Remember which to choose, right? See, it's plus 1.52. The dichromate is what? Dichromate is 1 plus 1.33. That means it's less positive. So obviously, I will put down here, this is positive. Okay, the winner takes all, right? It's negative. So after that, I know then the direction of electrons. The flow, direction of what? Electron flow. Okay, this will tell me direction of it, here to here. Okay, electron flow. Okay, that means this fellow here, remember, I forgot to say. See, in both of these beakers here, I must have all the ingredients. See, this chromium 6. Okay, it's chromium 6, It's dichromate, H plus and chromium 3. These all must be there. Same thing here, KMnO4, H plus and Mn2 must be there. All this is one system. They have to be there, both of them. Okay, this will go to this one. See, that's how you must write down. All must be there, right? Like here. Okay, see this whole equation here. Okay, right? In the little beaker here, right? And this, of course, is a platinum, right? Inside here, I must have this species 1.00 molar. I must have this species 1.00 molar. I must have this species 1.0. Of course, water is in excess. Okay, same thing as this KMnO4. Right? Right? In the beaker here, where I put my platinum here, my Pt. In the solution here, I must have 1 molar, 1 mole per degree of MnO4 minus. I have 1 molar of H plus. I must have 1 molar of Mn2 plus. All must there. So it can always go forward or go backwards. It can be a father or as a son. It has that capacity because the species are there. So in this case here, what is it going to behave like? So we know that, well, this system is more positive, KMnO4. So it'll be positive and here's negative. So the electrons going to flow here, right? So in this case here, if you talk about this case here, your dichromate is going to be undergoing what? Undergoing what? Undergoing oxidation. Okay? Sorry, reduction. oxidation point. It acts as a reducing agent with electron donor. You can mix up easily. Okay. So here, negative, no. So dichromate here is going to give electrons. It's negative. So here, so it's going to be going from here to here. Okay, because it's going to give out electrons. Yes, okay. So can be mixed up. Remember, this is negative, right? Negative. Okay, so it's going to give out electrons, right? So give electrons means what? Means what? Means it's going this way or this way. Okay, so going this way now, yeah? It's not, because it's going to give out these electrons. Okay, so the dichromate is not going to react, it's the chromium. The chromium 3 is going to be react. It's going to lose 3 electrons. You know. 2 moles here means lose 6 electrons. Okay, so here I need to write this one first, right? So, and I'm going to put this a negative. So you can see here, right? So it's a very strange little questions I propose. So I put on here 2 Cl3 plus, I repeat the whole thing, plus 7 water to give you Cl2O72 minus, plus 14 H plus 6 electrons, which is exactly how I did this one here. I just wrote it backwards because it's going to be supplying electrons, because why? It's negative poles in it. Okay, and if I write backwards here, I must change this sign to negative already if I want to do it by this way. So it's negative. Okay, 1.33. All right. Now to the positive pole, which is your manganate here, is receiving electrons. That means this fellow here, the plus 7 here is going to take the electrons. It's a king, man. It's a very powerful oxidizing here. It will rob the electrons. So this is what happened here, right? Now here. So this fellow here, right, will take 1 mole, because it's this plus 7. 1 mole to become Mn2 plus here must take 5 electrons. Okay? So whose electrons are this? Is your good friends, Cr3 plus electrons. Okay? Okay? So this means it's going forward here. So it's going forward here. I will repeat this whole thing here by forward here, and it's going to be positive 1.52. So here, you see, right? Mn O for minus here, right? Plus 8H plus here, and plus a 5E. All right, because this is, you just copy exactly from the data booklet, okay? And plus original raw value here, okay? So now to find the overall equation, I must make sure I balance off the electrons. Here's 6 electrons, here's 5 electrons. So 30 is the main common number. So 6 times 5, okay, times 5. So I put on the top here in blue color. 2 times 5, 10, 7 times 5, 35. Here's 5 on top here is, okay, right? I think something wrong here. Okay, 5 times 14 is 20. 5 times 40 is 14 is 20. Okay, 2 is 70 lah. Ayo, I got it wrong. 70, okay now. 70, see, I can make a mistake. 30, okay, there is something wrong there. Now, but I don't times this one remains the same because why? It's all 1 molar. So now to make this to 30 also, I time by 6 here. So 6 times is 6 here, all right, 6 here. And 6 times 8 is 42, 6 times 5 is 30 here. Okay, 6 is here, 6 times 4 is 24, all right? So now here I cancel, here 30 and 30 I cancel, okay? Right, so now I must overall. So 10 chromium, 10 here, 10 chromium 3 plus 10. Okay, do it again by yourself to prove you can do it, okay? Plus 6 here, okay? 6 here, MnO4 plus, okay? Now here is 35, here is 24. Water, I bring it over. So 35 minus 24, how much is it? 1 and 1, okay? Is it 1 and 1? Or I make a mistake. 24, okay? So 11 here. So I make a mistake. 11, okay, 11. Sorry about that. Okay, hurry. I always blame hurry. Okay, now here I made a mistake. It's wrong, okay? Here's 42. Here's 70. So it's on this side. So 70 minus 42, how much is it? It's 8, carry 1, 6, 20. So it's with 20. Over here, H plus, okay? Here's 70 here. So here's, so it's not over here. It should be over the side. Plus, how much? 28H plus, okay? I got it wrong just now. Okay? So easy to go wrong, right? So let's see, I rub this off. Okay. So nice, huh? Okay, rub it off. Okay, doesn't matter, right? Okay, got it down. So over this side, because the H plus is 70 over this side. So then this one here will be dichromate 5 and 6 of your Mn, okay, plus so here. So the voltage is this one here, 0.19. Okay, or you can write the other way. I tell you, I'm going to keep on doing this in your head after. Okay, this is the easiest way. Okay, sometimes don't write the over equation. This is very tedious. No, it's not here. Like I say, I can mess up by just forgetting some of the time something and then can forget it. So E cell is E reduction minus E oxidation. Very simple. Reduction first. Okay, so reduction is who? Reduction is a chemical form. Okay, originally, these are original values, raw values plus 1.52 minus origin values of dichromate is plus 1.33. So same, you get 0.19 volts. Okay, huh? So now you can use standard electrode potential to predict any cell, right? From Daniel cell to kingdom come cell, whatever. All right. Now the second one, of course, is to predict possibility of redox reaction. Now this is you done in Form 5 before, right? Remember, the reaction has got reagents, no products yet. Reactants or reagents, reactants only. Okay? If they react, if it's possible, it will give you your products. Okay? So products are not there. So in this case, I got 2 reagents, zinc and copper sulfate. So I got a solution of copper sulfate. Now we should do in Form 5, okay? Very simple one. You put copper sulfate here and you will do your AS. Okay, equals here, because it contains only copper 2 plus. It has no copper there. Remember this. Okay, no copper. So I put in powder zinc. Zinc powder metal, and there's no Zn2 plus here. Okay, remember, this is reactants. I put inside here. Will there be a reaction? Of course. You learn that zinc is more reactive than copper, so it will undergo displacement now. Okay, you will displace a copper 2 plus, and you normally give this equation here. But how did it come to being? So in Form 6, you learn, well, how do it's possible? Very simple. You use your standard electrode potential. You can predict. That's why it is to predict possibilities. Of course, this is quite simple. Zinc and copper 2 plus is quite simple. But how about other things which are you don't see before, or you have not met before, or unknown to you? You can still predict by using the table that's given in your data booklet. Lots of them there. 2-3 pages of them there. Okay, so how do you do it? Now, first of all, you must identify which is the reducing agent, which is the oxygen. Zinc, right, has to go to Zn2 plus. It cannot go to Zn minus 2. No, cannot. Stupid. No, stupid. That means the only reaction you can go to is zinc goes to Zn2 plus. Okay, there's only reaction. Okay, can 1 plus, but that one is not stable, okay? So we take a common thing, Zn2 plus, okay? So I write the equation. So this is the possibility, okay? So it goes in this way here. What is the value of the E naught? So I use my data booklet again. So zinc is in the last one because Zn, okay? Now, zinc here is Zn2 plus. I want this to go this direction. So going backwards, of course, it'd be positive, isn't it? No, okay, positive 0.76. So I put down here. I put the equation here and I put positive 0.76 volts. Okay? Good. Now for copper 2 plus cannot go lose electron, become copper 3 plus or copper 4 plus. It's stupid, isn't it? Of course, copper must be accepting electrons to go to copper. Okay, this is the common sense. So that's the only prerogative for you. Okay, so the possibility is is a redox reaction. Okay. So zinc undergoes oxidation, copper undergoes reduction. So somebody must give electrons, somebody must take electrons. So the point is, will it happen or not? So I put down the other equation, okay? copper 2 plus 2 electrochemistry. So I then look at my data booklet. Is there electrode potential for this? Of course there is. It's simple. So I look for copper 2 plus going to copper. Bingo. I can't take copper 1 plus because it's copper 1 plus, right? Okay. I can't take some because it's going to copper 1 plus. So copper 2 plus going to copper. Okay. So this direction, right? So positive, I can still use the raw one, plus 0.34. So here, plus 0.34. Okay. Right. All right. So I balance up the electrons the same. It's balanced by itself. So I add up this overall equation. Overall equation. So the N solid plus copper plus gives okay. Now I add on positive. This is the value. Positive means what? Feasible. Feasible means there's reaction. They normally ask you feasible or not. Give you the overall equation and of course the E cell. Simple as that. Okay, right? If it's negative means no reaction. Sometimes it will happen 2 steps that we see how it happens. Okay, so now here is one. There are a few questions I did so that it's easier for us can finish on time. See, right? These are passive questions. Use these E naught values, right? Which means the E naught values from where? This is standard electrode potential from where? From your data booklet. Okay, to predict whether a reaction will occur or not. Yeah, what reaction? Your redox reaction. When the following pairs of aqueous solution are mixed together. If reaction occurs, write the balance equation, the overall equation, and calculate the E cells. Yeah. Right now, Fe3 plus, you mix with chlorine, Cl minus. So imagine you got the two solutions here. Okay. Here's your Fe3 plus. No Fe2 plus and no Fe, okay, nothing there. Only Fe3 plus, iron 3 chloride, whatever. Here's your Cl minus. No Cl2. Okay? So I put it right here, or whatever I jumbo cut. The only way chlorine Cl minus can become Cl minus 2, isn't it? That's ridiculous. The only way it is to be oxidized or to lose electrons, become Cl2, isn't it? So this is the only way. So this is the most probable possible reaction. 2 Cl minus becomes Cl2 plus 2. Okay, so I put it down here. I check whether there is such an equation, whether there's such a let's say electrode potential Cl2 minus. We have got Cl2 going to Cl2 minus, right? See here, Cl2 going to Cl2 minus. So it's just the reverse, is it? Yeah. So I can put the reverse. I just change the sign minus. Okay. So here I am. So I put down here. See that going here and minus 1.36, very large value. Fe3 plus, so if this undergoes oxidation, right? This further must undergo reduction in, right? Of course, it can go to Fe solid, but normally, it won't go so far because 3 plus to 2 plus is easier than 3 plus to 1 plus and 3 plus, because 3 plus goes to 2 plus first and 2 plus go 1 plus and 1 plus go to Fe. So it's a long way. So normally go to the first easy one first. So 3 plus to 2 plus, can I have it or not? Yep. So common sense, okay? Common sense prevail. Okay, Fe, same one. This always occurs on Fe3 plus to Fe2 plus. Yeah, baby, here we are. Okay, so remember we're talking about 3 plus to 2 plus is a reduction, isn't it? Right? For chlorine Cl2 is right. So here, sorry, okay, now here is Cl minus to Cl2. Here is what undergoing what? Oxidation. Okay, oxidation, right? Okay, here, losing electrons, right? So now this one Fe3 plus to 2 plus, 3 plus to 2 plus, 3 plus to 2 plus. This one here, 3 plus to 2 plus here. Okay, 3 plus to 2 plus, correct. So it's plus 0.77. So 3 plus to 2 plus, 0.7. So here. So to do the reaction here, now there are two. This is the simplest way to do. I mean, use the equation. This will one kick can get 2 results, right? So I make sure I balance up the equation at times by 2 because I got 2 electrons here. So 2 Fe3 plus 2, so I cancel off the electrons here, right? So I don't change, I don't times this one here because both are 1 molar, so I don't change. So I add them up, 2 Fe3 plus, 2 Cl minus, and this one here. So Now, if add them up is minus. So minus means no reaction, not feasible. See now. So it won't happen. That's all. But that's what they want. No, they ask for this. No reaction 1 mark already. But of course, you need to work it out. Okay. But of course, there's a simplest way to do it. No. Okay. You use again. I told you something. I keep on repeating because it's so important. Later is very important. E reduction. Okay. Minus E. Sun is don't have to do anything on oxidation. Okay. Right. Reduction is what? In this case here is sun here. Okay. 3 plus to 2 plus. Okay. Reduction. And of course, you use the original value plus 0.77 minus oxidation is not, use this original value, okay, plus 1.36. You open up the thing, it becomes minus 0.59, right? Minus means what? Not feasible. Not feasible. That means no reaction. Okay. Right? This is a very useful thing. I will repeat again and again if I have to. Now the second one is cobalt 3 plus and Br minus. Okay. How do you start? Look at the thing first. Cobalt 3 plus may not be famous with you, or may not be usual or familiar with you, but you will do this later if you do a TN metals. Br minus is more familiar. So the only way Br minus can react because of Br minus to Br2, isn't it? Right? Can't go Br2 minus 3 minus is ridiculous, isn't it? So Br minus go Br2, right? So this is the only way it can proceed in a redox reaction. So it becomes oxidized. Okay, so we start with Br minus first. Okay, is there a electric potential for this? Not? Bingo, of course there is. It's famous, right? Remember? Right here, you have the reverse reaction happening. 2 Br minus become Br2 plus 2 electrons. Okay, reverse means I got a minus C0.107, 1 minus 0.07. So here I put down the reaction first, okay? Right? Is here. 2 Br minus go to here, so it's minus 1.07. Now cobalt. That means if this undergoes from here to here, remember oxidation, you know, oxidation, right? Lose electrons. So here, cobalt 3 plus here must undergo reduction. That means it must be accepted electrons. Okay, so 3 plus must become 2 plus. Of course, can go to cobalt 1 plus cobalt, but as I said, long way off. So normally the next one is 2 plus. So check 2 plus. Okay, you become more familiar when you do your TM method. Cobalt. See, cobalt here, the few one. Cobalt 2 plus to cobalt, no, okay? We don't want this one. We want this one here. So the choice is very important. Cobalt 3 plus, cobalt 2 plus, okay? Reduction. So I repeat this one here. Going forward here, it will be positive 1.82. So here, right? Going forward, undergoes reduction. Okay? Cobalt 3 plus electron goes here. 1.82 positive. Now, I want to kick these 2 electrons out. So I times all by 2. 2 and 2. I don't touch this. You keep it raw because why? All of them are 1 molar. So I cancel off the 2 electrons here, right? So voila, just nice. So I got 2 here, Br minus 2 CO, cobalt 3 plus, and Br2 and 2 some here. And you just add them up, positive. Feasible. See not? Feasible. That means it can occur. They ask you what? Give the E cell and also give the balance equation. So this is the answer. This one and this one here. Okay. Now this is the working, right? So here you can see the answer, 2 Br, right? See now, yeah. 2 Br minus cobalt, 2 cobalt 3 plus, and give you this one here, okay? And 0.75 volts, you know. 0.75 volts. Fantastic, isn't it? Okay. So this method, right? You give you everything, give you 2 answers, the equation and the voltage. But if you want to find the voltage alone, the E cell alone, use this one here. Easy. Later you see, they will just ask one here. Okay. So depends on the question. So you better learn both ways. E reduction minus E oxidation. So who is reduction? Obviously cobalt. Okay. Remember? Plus electrons. Okay. So it's plus 1.82 minus bromine. The original one is plus. Okay. So it's the same answer. Okay. So now the next one here, so you can see what I'm getting. It's quite simple, you know. Okay. Chromium 2 plus. If you have not seen before, actually in the lab, you can see this is a very nice color. This is a blue color, beautiful blue, royal blue. Come out a lot of times, but it's not very stable. It's easily oxidized to chromium 3 plus. Okay, Cr2 plus. Cr3 plus is very common in most experiments, but 2 plus is uncommon because it can be oxidized very easily by air to give Cr3 plus. It's blue color, this is green color. Okay, so TM metals can see beautiful colors over there. Okay, plus I2. Remember, okay, chromium will not be very familiar. When they put this together, will there be a redox reaction? I2 is charge 0. Of course, you have to go to I minus not. Can you go to I positive, isn't it? Okay, so I minus must be accepting electrons. So I2 here. Okay, this is not minus here. I don't know how the. Okay, so okay, so I2 will come I minus by 72 electrons. Okay, is there one in your table? I2, obviously, there's one here, right here. Okay, I2 plus 2 electrons gives one here, plus 0.54. So, of course, iodine becomes iodide. Okay, so I put the equation down here, number 1. Put the obvious reaction first. Okay, plus. Of course, if this, of course, is reduction. So, chromium 2 must undergo oxygen. So, Cl2 plus go to Cl3 plus. No, of course, can go 4 plus and 5 plus, but it's very difficult. Okay, so this one here, towards the 3 plus, is there electrode potential? Of course there is, otherwise they won't ask you. Chromium, there are a couple of things here. Chromium, see? Chromium 2 plus here, is it not? Chromium 2 plus here. So chromium 2 plus going to chromium 3 plus. It's just going to be reverse here. Okay, reverse here, I put positive. Okay, so here chromium 2 plus going to 3 plus. I put a positive, I change the positive sign. This, of course, is the 1 electron, so I balance electrons here. I times 2. Times 2. So the blue color, 2. Here's 2. And of course, 2 electrons here. So electrons cancel off. By this, I can write my equation, isn't it? Yeah, right? I got my equation here. Of course, I didn't write down here. How stupid I am. Okay, let me put down here equation, okay? So cancel this one here. So it's I2 plus 2 CR 2 plus. You know, I spent a lot of time doing this. I tell you, 2 hours preparing, man. No joke, man. I tell you, you first here. Go to 2I minus plus what? 2Cr3 plus. And of course, the E cell is how much I did you here before. Okay, right? Just add them up. It's positive 0.95 volts. Okay, is it right? Yeah. Okay, 0.95. Yeah, here's it. Okay, let's see the answer. Oh, correct, man. See, of course, correct lah. Okay, see, I2, 2CR, okay, and of course, this one here. 1 mark. Of course, 0.95, yeah. Okay, so here we are. Okay, why is it coming up? I don't know. Okay, so remember, all right, I said you can do the other one also. Okay, right? This method here, E cell equals to E reduction minus K. You get the same answer. Okay, right? So next one here. Now, these are all same, the same thing. I just want to go quickly because time is catching up with us. I need to finish off the second part there. Okay, now same thing. Potassium magnet and potassium chromate. See, these two are very common oxidizing agents. So that's why I put them in this special cell, just in case they ask you, who knows not here, right? Too powerful. These are very common reagents in the lab. So if it happens like this in a half cell, in a cell, you can actually do it, right? But of course, I say, perfect practice makes perfect. So you need to be perfect in everything you do. Otherwise, you will just, I will just flip on here, flip on there. You must be perfect, must aim at perfection. Otherwise, cannot. A levels, no joke. So now, right, I both use an acidic solution. I say why? Because always got H plus 1. Okay, you got H plus 1. The dichromate, okay. So now using the data in the data booklet, of course, using your electrode potential, standard, okay. Write either ionic or full equation. Ionic is easier because why? In the data booklet, always given ionic on it. It's very mafan, very difficult. Fraction below, blah, 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 of course here. Now you need to know which is the reacting substance. KMO4 will give you K plus and K. K plus is stable. Why got a 2,888? So this is the fellow here. This is the reactive fellow here. Everything here, of course, is stable, can react as well, but this is the common one. So, okay, so going to see 2 of them, all right? MnO4 and Fe. Now, obviously, you have to come to this from your practice, perfect practice. You know that, F So MnO4, if it's going to be oxidizing agent, right? Agent means it's going to undergo reduction, right? Right? That means it's going to accept electrons, right? Accept electrons, which means this one here, Mn here is your +7. It's going to go to +2. Okay? It's going to accept electrons, huh? So Fe2 plus must of course give electrons, no choice, right? Fe3 plus. So you choose the right equations from here. So first thing, of course, you need to know your chemistry. You can just go in cha cha. What is simply put, you fail, man. I tell you. So this one here. Okay, right. Remember, don't use this one. This one don't use. If you use one here because this is actually for alkali conditions. Okay, in alkali or not enough acid, you get this one here. This is a dark brown PPT, okay, if you've done before in your experiments. So this one here, okay, remember, it's very powerful oxidizing agent, which means it's a powerful electron acceptor. 5, okay? So you repeat this one here and plus 1.52. So this is what you get here, all right? This equation here, I've done it 1,000 times already, all right, okay? And every 2 plus, every 3 plus, I also done it 1,000 times already, okay? So remember, here is 5 electrons, here's 1 electron, so I times this by 5. So 5 here, 5 here, 5 here. I don't times this is the raw. Cannot. Why? Because all the solutions here is 1 molar. So I can use 10 liters, 1,000 liters. It still is one mole per dm cube. So I cancel off the electrons here. I got my equation there. 5. Was it 1 mole? This is what you did for titrations here, and so forth, so forth. Of course, here minus 1 is positive. Positive means what? Feasible. Right? They ask you for the ionic equation only. They don't ask you for this one here. All right? That means it will happen. All right? So look at the answer here. Okay? Right. See. Okay? So you can use the other one here, but not good. Okay? See that? MnO4. Okay? 1 mole, 8H plus, 5 moles of this. Okay? 1 mole of this, 5 moles of Fe3 plus, and 4 moles of water. Voila. All the species and products, 1 mark. Balancing, 1 mark, 2 marks. Simple, isn't it? Actually, they should ask the E not give 1 more mark. Yeah, this further. Never mind. So now this dichromate with a SO2. SO2 is well known for what? AS is a good reducing agent. Good reducing agent. It's the only reducing agent gas, or gas which is a reducing agent, reducing gas. That means this is going to be oxidized. Okay, dichromate. Potassium, no, dichromate is +6 here, going to be reduced to +3. Orange to green color. This is green color. You know very well. So, of course, sulfur dioxide will undergo oxidation. Remember, sulfur is +4, right? And this is +6 here. So it must be losing electrons here. Undergoing oxidation. Okay, like you can see here, you choose your data booklet from here. Chromate, dichromate. Okay, I'm going to be faster so you can refer later. Okay, right here. Okay, Cr2O72 minus plus electrons. Okay, Cr3 plus. Okay, so this is the first one here. All right, first one here. The second, sulfur dioxide. It's tricky because you need to find where is it. So look for S lah. The S here. Okay, now which part is it on? Of course, if it's going to be an electron donor, it must be here. Okay, all these fellows here, these side fellows here are oxidizing agent. Because they are electron acceptors. All these fellows here are what? Reducing agents. Because they are electron donors. So this is a reducing agent plus water goes like a minus sign here. Okay, so go to sulfate plus 2 electrons plus 4H. Okay, so it's on here, see now. Okay, plus water, must put the water here plus SO4 and it's minus. Now, why minus? You can see here, okay, the other way is positive, isn't it? Forward is positive, backward is negative. Okay, so here you make sure the number of electrons is 6 here, right? Here's 2, so I times this by 3. So here's 3. Okay, here's 6 here. Here's 3 here, and this 12, okay, and this 6, so you cancel the electrons here. Yep. So then you write balance, okay, 3 moles of this one plus 1 mole of chromium, dichromate, plus now here again, see, let me mix it up. 14 and 12 here. You bring over here 2H plus. Yeah. Okay. Water here got 6 and here got 7. So you bring it over here. Right? So it's 1 mole here. Okay. And of course, you add this up now, plus. That means it's going to reaction. Now, you can check it out. No, here, 2H plus, 2H. Okay, right? Oxygen is quite tedious. No, here's what? Here's 6 plus 7, 13. Is it 12? Okay, 12, 13 now. Okay, so you can see the answer here. 1 mole of chromium, dichromate, 2 moles of H plus, 3 moles of sulfur dioxide, 2 moles of chromium, 3 plus, 2 moles of this, and 1 mole. Okay, this is it, right? This is how you write your equation. Okay, so I put it easy for you. Okay, so now this one is a bit tricky here. Okay, we got a bit more time. All right, now here is H2O2 and Ki. H2O2 is very important here. The H2O2 is like, is two-phase. It can act as a father, act as a son. Okay, it can act as an oxidation agent, act as a reducing agent. Now, which one is it? You see here. Okay, I need you a bit more time. Now, it's very important here. See, H2O2, hydrogen peroxide, on this side. I tell you, if it's on this side, it's a what? It's an oxidizing agent. Oxidizing agent. Because one is an electron acceptor. On this side, is a reducing agent. Because it's what? It's a donor of electrons. Okay, it's a donor of electrons. So which one do we choose? Okay, all right, which one to choose? Very important. Now here, it will depend on your equation here. Now, Ki, obviously, Ki give you I minus. I minus cannot go to I2 minus. It can go to I, is not. It means that it's going to undergo what? Oxidation. That means I minus is going to I2 0. Okay, that means it's going to undergo what? Oxidation. That means H2O2 will undergo what? Reduction. That means it's going to be an oxidizing agent now. Okay, it's going to accept electrons. If you consider agent that does accept electrons, it has to, because both cannot give electrons. So for I minus to react, you must go to I2. So you choose H2O2 to accept electrons. So which one will you choose? Remember, accept electrons. So remember that here, see, accept electrons. Here, it will be donate electrons now. So you choose this one here. So the choice is very important for hydrogen peroxide. So this one here, H2O2 plus 2H plus 2E. So you can see here, right? I choose one here, plus 2, okay? So it's plus 1.77. You can see here, plus 1.77. Okay, this going forward here is plus 1.77. Okay, right? So once I chose which is oxidation, which is reduction, right? I can balance the electrons. 2 electrons won't self-balance off. So I put down here 2, this whole thing here, can see here. So it's plus 1.23. Okay, so they ask you to calculate the electric potentials. Construct redox rate. That means both on this one here and this one here. Okay, now the answer. Right here, you can see here. Put smaller, can see both. Okay, see that here. H2O2, 1 more here. 2I minus, 2I minus here. 2H plus here. Oh, correct, fantastic. I2 here, I2 here. 2 water here, 2 water here. Okay, of course, you forget the whole one. Okay, now what's the voltage? Plus 1, 2, 3. Plus 1, 2, 3. Fantastic. Both answers. I told you already, this way is easier. You can get both the answers out. But you do this way also can, but you have to work this out yourself. Okay. E redox, reduction minus E oxidation. Reduction. Down here. Okay. Plus 1.77 minus this original is plus. Okay. Same answer. Okay. Okay. Now let's the 2 more. I look at the time. We can do it. Very simple. Okay, Cl2, both are gases, okay, but in solutions. So Cl2 and SO2, I told you which is the obvious one. Of course, Cl2 becomes Cl minus 1, okay? Cl2 cannot become Cl positive. Yes, you can in organic chemistry, but it cannot. So this is undergoing reduction. This is oxidation agent, it's undergoing reduction. That means SO2 will undergo what? Oxidation. Plus 6 to plus 4, to plus 6 here. Okay, so again, you get from the potential here, Cl2 to Cl here, you can see okay, Cl2. Okay, I'm going a bit slow for you, but Cl, okay, right, plus 1.36, okay, right, 1.36, okay. Now SO2 undergoing what? Oxidation, that means it's an electron donor, all right, so you make sure you got right here. So it's over this side, over the right hand side here, SO2, 0. All right, going this way here. So using this very important, you know, going here, get sulfate, so we minus 1.017, I see. Okay, here. Okay, so two electrons here, can cancel off both them. So Cl2, everything is okay, no times, okay, right? So you can get both answers here. You can see here, Cl2, Cl2. Okay, Cl2. SO2, SO2, 2 water, 2 water, 2 Cl minus, 2 Cl minus, SO4, 1 mole, and 4. And of course, this answer is what? How much is it? How much is this? 0.019. Okay, 0. Okay, correct. Now the last one here is pretty, well, very nice here. Now they put here for special consideration. Use the data for data model to predict likely product of the reaction between I2 and the tin metal. Tin metal. Both of them are neutral. I2, tin metal. Right, a balance going for the reaction. Now here important, the tin, you see there are a couple of things here which are important, can go to so tin. See, tin can go to SN2 plus, can go to SN2 plus, can go to SN4 plus. Same as vanadium, can go to V2 plus, can go to 3 plus, can go to 4 plus, and can go to 5 plus. Okay, so this two take note, came up before. Okay, tin and vanadium. Okay, they have to tell you one actually, otherwise, so you have to learn the practice. Okay, so can tin be oxidized to 4 plus or 2 plus by iodine? Okay, now iodine here. So the iodine here, okay, iodine here is able to take electrons away. Okay, go here from this side from tin. So we got to do step by step, 2 steps here. All right, can see here. I did all here already. So the first thing, of course, remember I2 must become I minus. I2 cannot go to I plus. Right, very difficult. Okay, I2 to I charge 0 to I minus. So it's except 2 electrons here. Right, so now this is the voltage here, 0.54. Why is 0.54 here? Iodine, see, 0.54 is positive. Why is it going forward? It's not plus electrons. So, okay, here, I got it right here. So where does electron come from? From tin. So tin is oxidized first. See, step by step, I can go to 4 plus one shot. Go to this one first, SN2 plus. Okay, so this one here, SN2, tin go to SN2 plus, which means it's the reverse of here. All right, see here, tin. Right, tin is oxidized to SN2 plus. Okay, that means it's going to be positive 0.14. Yeah, means I draw like that here. So you can see here. Okay, so tin going to here. Okay, it's positive 0.14. So I add them up. Okay, I 2 electrons here cancels. So it's I2 plus Sn give you 2I minus and Sn2 plus N. And it's positive. That means boleh. That means iodine can oxidize your tin to tin 2 plus. Right? But the point is, can iodine, of course, iodine here is the excess. You must come to that conclusion. Can iodine continue to oxidize Sn2 plus to Sn4 plus? So I put again iodine, right? Go to I minus, because I minus already happy already. Is married already, got no need to tackle girls anymore. Okay, SN2 plus. Can it be further oxidized now? So I put this down here. Now this is the same one as this here. SN2 plus to SN4 plus. All right, and let's see here. All right, can this be further oxidized now? Okay, see there's direction here. Plus, let me see, it's going to be minus 0.15. All right, so here, okay, go this way, minus here. So I got the electrons here 2, and here I2, SN2 plus go to this one here, 4 plus now. Okay. Oh, it's positive, you know. This and this is positive. That means feasible. That means it can go to SN can go to 2 plus by oxidizing by what? Oxidation, oxidize by I2. So here it says, well, since okay, it's only 1 mark. Right? So here, since this one here oxidized with tin will oxidize to SN4 plus. Okay, you can show the result already. Okay, and so forth. So you do this out the full marks here. So they ask you for the overall equation. So what's the overall equation? Very simple. Use this one here and this one here. The two equations here, which means what? I2 plus Sn to give you 2I minus plus Sn2 plus. Okay, the first one. Second one is I2 plus Sn2 minus goes to what? 2I minus plus what? Sn4 minus 4 plus. So you add them up, right? You add them up. Okay. So here you cancel this one here, cancel this one here, right? So you got 2 I2 plus, right? Sn goes to what? 4. Sorry here. Yeah. 4I minus plus Sn4 plus. Can read it. Because this one is actually what? Sn4 plus 4I minus. Is that clear? Okay. So I cannot do everything here, but okay, one more before we end. Okay, this one here, right? Because the rest of them is okay. Okay, what? Time. Okay, here one more. Okay. See, all of them are the same. Here, use the data bottle to calculate the static potential for Cr2 plus this one here. Okay, I mean these two reactions. Okay, construct the balance equation. So remember Cr2 plus, now this plus 6, this plus 2. So the point, would there be a reaction? Now you must learn to look, you must learn to say Cr2 plus here, 2 plus here, say Cr2 plus here, Cr2 plus here. Okay, Cr2 plus here, see. We'll put blue color here, let's kind of see. Cr2 plus here. Okay, you can go to Cr3 plus. That means it undergoes what? Oxidation. Cr207 here can go to Cr3 plus. So these are common, by reduction. Okay. That means this and this can react, what? Because it's a redox reaction. See, but the point is it feasible or not? So you put these two fellows here in the reaction. Okay, that's what I did. Okay. So Cr2 plus going to Cr3 plus is the E0 value. Cr207 going to Cr3 plus is the value. Okay. So again, I times all and I figure out, and it gives me a positive value. That means feasible. I told you guys, okay, equation. So this is the equation here. Okay, right? You can do it for yourself, okay? See, right? 6 Cr2 plus here. One of them here. 14 here, right? And 8 here. 8 Cr3 plus. Why got 7? And Cr. Okay, 6. Oh, sorry. Here's 2. I didn't say here's 2 here. So it should be 8. See? I can mix up. So 8, 7 water. Okay, right? And the voltage here is, see, 1.0. Right? The color change on orange. They ask you, describe the color change. Describe what you see in blue. Blue is blue. So 3 plus added to this one here. This is what color? Orange. Change to what? Green. See? Because Cr3 plus is green. Cannot. Okay. Can. I think now this well, I think we did before, okay. So I have not finished the comparison yet. Never mind. Okay. So we would do the last part next time here, the strengths. Right. So goodbye. Thanks for watching, and please go over this one again because it's very important, this topic here. All right. So goodbye, and let me see how can I stop this thing here. Stop recording.